What's up guys, and welcome to this video on question 7 of the 2016 final exam. It has to do with electric circuits and is worth 27 marks. Okay, let's get straight into it. A circuit that consists of a battery with an EMF of 26 volts. Okay, so the EMF is equal to 26 volts and an unknown internal resistance R, 3 resistors and an ammeter and voltmeter is set up as shown below. Cool stuff. Yeah. Okay, so we start off with a definition. 7.1.1. Define a resistance. Okay, so resistance is a material's opposition to electric current. Okay, or you could say to the flow of electric current. Okay, and we get 2 marks for that definition. Okay, 7.1.2 says calculate the effective resistance of the circuit. Okay, so the effective resistance of the entire circuit. Okay, so I'm going to deal with this branch right here first. I'm going to say that's 1. Okay, so I'm going to say, so that's a parallel branch, right? So I'm going to say 1 over R parallel is equal to 1 over, let's say this is, let's do this. Let's say that's a resistor 1, this is 2, and this is 3. 1 over R1 plus 1 over R2. So 1 over R parallel is equal to 1 over 6 plus 1 over 10. So the only unknown here is R parallel. So we can solve for that, and R parallel is equal to 3,75 units of ohms. Okay, so that's the resistance over here in the circle. Okay, but there's a resistor on the outside, right? But that is in series. So R total is going to be equal to R parallel plus R1. Okay, so we have 3,75 plus the resistor had a resistance of 4 ohms plus 4, so our total comes to 7,75 units of ohms. Okay, so I hope that makes sense. Yeah. Okay, I'm also going to just draw the equivalent circuit because that might come become useful. Okay, so we have the cells. Okay, I'm just going to do it on the side very roughly. We have the resistance of 7,75 ohms. Then we have an ammeter. Then we have nothing else, and we've got the voltmeter across there. Okay, just because that might be useful, maybe not, but we'll find out. Okay, so the ammeter measures a current of 3 amps with the circuit connected as shown. Define current. Okay, so another definition, 7.1.3, current is the rate of flow of charge. Okay, and we get 2 marks for that. Okay, then it says calculate the potential difference that will be recorded by the voltmeter. Okay, so we want the potential difference that will be calculated by the voltmeter. Okay, so for this, I'm going to use the equivalent circuit that I drew. So for question 7.1.4, I'm going to say that V is equal to the R total times the current. Okay, so V is equal to R total, which we said was 7,75, and the current was given as 3 amps. So we get that V is equal to 23,25 units of volts. Okay, and we get ourselves 3 marks for that. Okay, so then it says, hence determine the internal resistance of the battery. Okay, so the voltmeter reading was 23,25. Okay, so question 7.1.5, I'm going to use the equation that the voltage is equal to the EMF minus the current times the internal resistance. Okay, the voltage we measured as 23,25 is equal to the EMF, which was given as 26. okay, 26, minus the current, which we know is 3 amps, times the internal resistance. Okay, the only unknown here is R, so we can solve for R, and R comes out as being 0.92 units of ohms. Okay. Okay, so I hope everything made sense there. Okay, so sometimes resistors burn out while in operation. Okay, that's true. So it says, describe what would happen to the reading on the voltmeter if the 6 ohm resistor burned out. Okay, use a suitable equation to explain, basically. Okay, so first we have to ask ourselves, okay, so which resistor? So the 6 ohm resistor gets burnt out. Okay, so let's get rid of that 6 ohm resistor. So what does our circuit now look like? Okay, so what we have is we have something like this, right? We've got 10 ohms and 4 ohms in series now, so we have 14 ohms, and we still have the ammeter, and we have a voltmeter. Okay, so the question says, what happens to the voltmeter reading? Okay, so let's see what's happened. Okay, so the total resistance of the circuit is increased, right? Before we had 7.75 ohms, now it is 14 ohms. So we can say for question 7.16, the total resistance in the circuit has increased. Okay, therefore the current, the total current decreases, right? Because there's more resistance now. Therefore, the total current decreases. Okay, does that make sense? There's a higher resistance, so now less current is able to flow. Okay, so then we can say, but using V is equal to the EMF minus IR. Okay, so if we have the EMF is a constant, okay, the internal resistance is a constant, and I has gone down, right? So that means the voltmeter reading will go up. So therefore, the voltage reading increases. Okay, so I hope you guys followed that. Okay, so just to summarize, okay, so basically the 6 ohm resistor breaks, so burns out. So therefore, we're left with just this. Let's go from positive, just this circuit right here. There's no parallel branch, so everything is in series. So we're left with this diagram that I drew right here. And if we compare the resistance, we have 14 ohms compared to 7.75 ohms, which means our total resistance has increased in the circuit, and therefore the total current has now decreased. Okay, and then we use our equation and we say that the EMF for the battery is the same as is constant, and the internal resistance for the battery is also constant, and the current has gone down. So if you have a constant minus a smaller number, the voltage will now go up. Okay, and we get 4 marks for that. Okay, so predict what the reading on the voltmeter would be if the 4 ohm if the 4 ohm resistor burned out. Okay, so this time the 4 ohm resistor burns out. Okay, so now we still have that, but now this gets burnt out. Okay, so if that burns out, basically we have no current flowing. The I is equal to 0. Okay, no current can flow because there is a open circuit here. Basically nothing's the resistor is burnt out, so current can't flow. So for question 7, let's do it somewhere here, 7.1.7, we can say that the I total is equal to 0, right? So that means, or 0 amps, so that means if we use the equation, so using the same equation, V equals the EMF minus IR, because remember it's asking what will be the voltmeter reading. Okay, so the EMF is the same, so the EMF will be equal to 26 minus 0. So our voltmeter reading is equal to 26 volts. Okay, I hope that makes sense. So basically there's no lost voltage. Okay. Okay, so the next question, a little bit of reading. Okay, so Chris finds an unlabeled battery in the lab and needs to use it in a circuit. However, it is necessary to determine the EMF and internal resistance to decide if the battery is suitable. Okay, so I'm going to focus on the words EMF and R. Okay, Chris connects the unlabeled battery to a 2 ohm resistor and measures a current of 2 amps through the resistor. Okay, he then connects, so I'm going to say this is R1 and that's I1. He then connects a battery to a resistor R2 and measures a current of I2 is equal to 3 amps. Calculate the, okay, so basically calculate what I identified before, internal resistance and the EMF. Okay, so how are we going to do this? We're going to run two scenarios, right? Okay, so again, the governing equation is what we have been using before, that it is the EMF is equal to IR plus I times big R. Okay, so this is the same as V equals, what did we have? V equals the EMF minus IR, right? Minus I times small r. Okay, let me just actually get you to that point, to the equation we landed up with. Okay, so then V is equal to I times the external resistance. Okay, so that's equal to the EMF minus I times the small resistance or the internal resistance. So manipulate this equation to get the EMF as the subject of the formula. So we have EMF is equal to IR plus I times external resistance. Okay, so that's how I got that equation before. Okay, so now I'm going to use scenario 1. Okay, so I don't know what the EMF is, so I'm going to say the EMF is equal to I1. I1 was 2 amps times R plus I2, times I1 again, so it's 2 times R, which was the external, which is 2. External resistance. Okay, and then for situation 2 we have EMF is equal to I2 this time, so I2 is 3 amps times R plus I2 again, so 3 amps times the resistance of this, which was 1. Okay, so now what I'm going to do is I'm going to take this, I'm going to take 1, or actually I can just do this. I can just say 1 minus 2, okay, is going to be, so, okay, not, yeah, I can actually do that. Okay, so let's actually do that. So let's say, okay, so we can say 1 minus 2, so equation 1 minus 2, okay, so EMF minus EMF is 0, which is equal to 2R minus 3R, which is minus R, okay, which is equal to 4, or plus 4 minus 3, which is 1. So plus 1. So R, small internal resistance, is equal to 1 ohm. Okay, and then to calculate the EMF, I just need to substitute. So sub into sub R into either 1 or 2. This time I'll just pick 1, and we get the following. We get that the EMF is equal to 2 times R, which we just calculated, is 1, plus 2 times 2. Okay, so we're left with 4 plus 2, so the EMF is equal to 6 units of volt. Okay, so I hope that made sense. Okay, a nice, I wouldn't say it's too difficult, but a nice question, and it's worth 5 marks, so it's worth it in the end. And yeah, so that's this question, guys. A little bit of thinking here and there, but generally not too difficult. I hope you guys were able to follow a little bit of theory. Yeah, thanks guys, and you get your 27 marks. Thanks for watching, guys. Cheers.